j e to the minus I over h bar h hat delta t qj. And the point is for small delta t, so let's just say precisely to order delta t. So I'm going to ignore anything that's got delta t squared in it. And this will be precise enough when we take delta t to 0. So to order delta t, I've got an exponential of this thing. So all I do is expand it. So you know e to the x, you have a Taylor series or Maclaurin series, 1 plus x plus a half x squared and so on. So this thing here is 1 plus that thing. And then the next term obviously contains the delta t squared. So I'll just ignore that. So to order delta t squared, that's my 1, which, because it's operator, it's an identity operator. It's like matrix 1. And then I take this factor in here, minus I over h bar h hat delta t. And then I don't care about the rest of it because it all contains delta t squared. Okay, so we can work this thing out. So we get, well, the first bit with the identity, I get this qj plus 1. Identity on qj just gives me the same state back. So the first one is just this product qj plus 1 qj. And then here, well, I've got some numbers minus I over h bar, and this delta t is just a number. And then I've got the Hamiltonian. So we'll just assume standard Hamiltonian. So it will be 1 over twice the mass, momentum squared. So remember, this momentum is an operator, quantum mechanics. And then plus an arbitrary potential. So again, the whole thing is an operator, so these q's in principle are operators. Okay, and, well, then I can split this up. Now, the point is, the operator Q, so what's this state here? This is a state of definite position Qj. This is a position eigenstate. So the operator Q acting on that just brings out that eigenvalue. So in other words, the operator here acting on a state with definite position just becomes that number for the position. So that's what we mean by position eigenstate. Just like if you have an energy eigenstate, the Hamiltonian acting on that eigenstate is equal to energy times the eigenstate. So this just becomes a function v of qj, so this particular qj here. And then, well, that will just be a function, so we can bring it out, it's just a number. And then again, we've got then a product of qj plus 1 with qj, so, which is the same as this form. So we get qj plus 1 with qj, and we get 1, and then we've got minus I delta t over h bar v of qj. And then we're left with minus I delta t over, now we've got 2m with the h bar here. So we've got this momentum operator in here, and of course, that doesn't immediately simplify because the state of definite position doesn't have any definite momentum, and so we can't immediately simplify that. So this is what we have. So this is working this out to order delta t. Okay, now what we want to do is to write this inner product here and this inner product here in some nice way. Okay, so this qj plus 1 qj. So we know already, we've said that's the delta function. So it's delta of qj plus 1 minus qj. And then I'm going to write that in a particular way. So into more detail, but okay, let me just write down these. If people want to ask, we can do this afterwards since I'm a little short of my time. And it's on the handout I'm giving out essentially how to do this. So 1 over 2 pi h bar integral dp, make sure I get the factor right, e to the I over h bar p times the difference of the q's. Okay, so I mean this is the sort of form that comes up when you do Fourier transforms and things like that. But again, I can explain a little more afterwards. Okay, and the other one with the p is there. Well, I want to evaluate this operator. I don't like having an operator in this expression. I want to get some numbers. So obviously, if I had a momentum eigenstate, then P acting on the momentum eigenstate just gives me that momentum. So what I do here is I stick in the identity operator. But now, in this way, so I'm integrating over, these are now momentum eigenstates. Of course, the notation in quantum mechanics, you have to know what the notation means before you understand these things. So this isn't position eigenstates at all now. These are momentum eigenstates. So basically the rule is I can sum like this. So I had the one before where I summed over position eigenstates, but I can sum over any complete set of eigenstates. So this is just some different basis I can choose. Rather than choosing position eigenstates, I choose momentum eigenstates as a basis, and I sum over all of these. So it's just like a change of basis. I put that in here. Okay, so now this one just gives me a factor of p squared. And then I'll have the inner product qj plus 1 with p multiplied by the inner product of p with qj. Okay, so again, I haven't reminded you, but these are just exponentials. So we could integral p, again, make sure I get the factor right, p squared over 2 pi h bar e to the I. So they're exponentials of p times the q, essentially. So to the I over h bar p, and then it's the same factor as up there, qj plus 1 minus qj. Sorry, I'm squeezing that in there. Yes, it's this exponential, but it's exactly that one there, if you can't read my writing. Okay, so again, I can explain all where this comes from, and it's on the handout. But let's move on just now, just using these results. So in the last 5 minutes, we can finish this off. So you notice in this inner product and this inner product, both times an integral over p, and we've got this factor of e to the I over h bar p qj plus 1 minus qj. So the whole thing becomes integral over p. Okay, let's stick the 1 over 2 pi h bar at the front. And then the difference is then this factor here, and then this bit here comes along with a p squared from there. So if you just collect all these terms, it looks a little messy, but we've got 1 minus I delta t over h bar v of qj plus, so the minus I delta t over h bar plus p squared over 2m. Okay, so it's all a bit messy. And, okay, well, have we got anywhere? Well, again, remember, we're only working to linear order in this delta t. So there would be other terms with delta t squared and so on. But we said we don't care about them because we're going to take delta t to be very small. And, well, I didn't justify it precisely, but take my word that you don't need to worry about these higher order terms. You can look into it if you want to be more careful. So basically, to that order, though, I've got 1 plus something with the linear factor of delta t, so I can call it, again, an exponential. So to that order, so this 1 over 2 pi h bar integral dp, I can say this is the exponential of that factor, because when I expand it, get 1 plus that factor, and then everything else is of order delta t squared. So and I don't care about these things. So to that approximation, this is exponential then of that. So, and of course the exponential combines then with this exponent as well. So we get their factors in common are I over h bar delta t. So which way have I done it? I've taken a minus sign. So minus I over h bar delta t, you can take as a common factor. And we get p squared over 2m plus v of qj. And then I'll get minus p. Now, I've taken a delta t out here, so that means I should have qj plus 1 minus qj over delta t to make this right. Now, for very small delta t, then that's just the velocity. That's the definition of a derivative. I've taken start at position qj, and I've timed delta t later. I'm at this position. I take the difference, divide by delta t. So I'll just call that q dot for the derivative at j. And, okay. Now, what's good about that? Well, looks messy, but just think about the important points. You're integrating overall p, and we've got an exponential. So everything that's not p is just a constant in here, okay? So the qj's, qj dots, m, so on, they're just constants. They're independent of p. P is just some variable that we're choosing to integrate over. And we have an exponential of a quadratic, because at most I've got a p squared here, which is linear in p, and the rest is all constant. So you probably don't remember in your head, but you probably have seen how to integrate quadratics. The point is, of course, whenever I write this, I mean from minus infinity to plus infinity. So you can't do the indefinite integral, but you can integrate from over the whole range. So this is a quadratic. So the way to do it, and okay, I better not try and explain now. So on the handout, but basically you complete the square in p. So you take this as some factor, and then p plus something all squared, and then you can do this Gaussian integration. So that's on one of the handouts if you need reminded of that. And that does the integral over p and gets rid of all the p. So what you get from that, so this is a good exercise for you. Gaussian integration. It's just to follow this through to make sure you agree. You should end up with, sorry, squeezing it in too much. Minus im over 2 pi h bar delta t under a square root times an exponential of I delta t